So yeah, so what I want to talk about is, I've nicknamed it defects with character, zero energy Majorana modes in condensed matter systems, and the defects with character are because these Majorana modes occur at defects, as we'll see. So okay, so what is all this about? Let's see, this is, I think, the right way to go ahead. Yes. Okay, so what I'm going to be talking about today is something that people have been fascinated with for quite some time now. It's largely a theoretical concept, but there's some experimental evidence for it, and people are trying to zero in on it experimentally, and it certainly has attracted a lot of attention. So what are these things? So these localized zero energy Majorana modes, they're extra kind of zero energy degrees of freedom that have been at least proposed to occur in certain special correlated electron systems, both one and two-dimensional systems. And these are low energy or zero energy degrees of freedom that occur at isolated points, and these points are defects in the of a type that I'll explain. And if these Majorana modes occur, then they should have some very peculiar properties, and they've generated a lot of interest. And as I said, it's only modest experimental evidence so far, but my main thing is mostly going to be talking about the theory. I'll say a few things about the experimental status at the end, and hope to just convey what the basic ideas are without giving all of the details, which get a little complicated. So first I'm going to talk about what are the peculiar properties of localized Majorana modes, if they can be found, and then we'll talk a little bit about where we might find such modes. But I'm going to mostly be talking about one proposal, which is the leading candidate currently, or the most promising in the near future, which is these are what I'll call hybrid wires. They're basically combinations of a semiconductor nanowire, which has to have strong spin-orbit interactions, that's coupled by proximity effect to a nearby ordinary superconductor. There are other ways of doing it, but this is the way I'll be talking about. Then we first talk about an individual wire, and then talk about a network of wires connected by junctions, which we need in order to do interesting things with these Majorana, which means manipulating the sites on which these things sit. And then after that, I will say a little bit. There'll be very little math up to this point. Then we'll talk a little bit more about the mathematical description of these modes, conditions where you would find them in a hybrid nanowire, and some comments on the experimental situation. So, okay, so what's the defining property of one of these localized modes? So first of all, you have to start with a parent system, which, in the absence of any defects, and without, if we're far from the boundary, it has a finite, let's say, it could be an infinite system without boundaries, or a system on a torus or a sphere. So it would have a finite energy gap for electronic excitation. So there's just there's a ground state above that ground state to produce excitations, cost you some finite amount of energy. But on the other hand, if you take the same system and you put certain kinds of defects in them, then you get very low energy, essentially zero energy, extra states. And the weird thing is that if you have n defects, n separated point defects, the ground state of the system is degenerate, and it has 2 to the n over 2 degrees of freedom. So 1/2 of the degree of freedom for each of these states. And furthermore, the ground state degeneracy is very robust. You can perturb things locally and nothing happens to it. And I want to contrast this with something which you're much more familiar with. If I have, say, an insulator which has some magnetic impurities, so there's spins, localized spins in the system, then there's a degree of freedom 1 degree of freedom, a spin and a half, let's say, in the simplest case, degree of freedom for each spin, and that can be either up or down. So we have a Hilbert space, with the basis of the Hilbert space, which would be the product of these up and down states. And so there's obviously a low energy Hilbert space, which is dimension 2 to the n. Okay, and we can, that's basis states, we can specify the basis states in the Hilbert space by choosing spin up or spin down at each site. Now, if you don't have a magnetic field, and if there's no interaction between the spins, then these states are completely degenerate in energy. So we have a degeneracy. On the other hand, it's not robust, because if you take into account, say, if I take into account exchange interactions between the degenerate, these states, these, of course, these to the n states will be split, but exchange energies, of course, fall off exponentially with distance. And so if spins are in an insulator and the distance between them is large compared to this exponential fall off, then the splitting can be completely negligible if the spins are far apart. So if there was nothing but exchange interactions, we would consider this rather robust. Because in practice, if they're very far apart, there's not much you can do to split this energy. On the other hand, spins have other kinds of interactions. So, for example, they have a magnetic moment. And that means it's a dipole moment. That's an observable quantity. And that means that since it's observable, it's because it's coupled to some local magnetic field. And if I have any kind of magnetic field that varies from one point to another, it's going to split these energies by a finite amount. And even if I have no external magnetic field, then they're dipole-dipole interactions, which will fall off only as 1 over r cubed, not exponentially. So we would say this is not robust. That's what we mean by not robust. Now with the Majorana modes, as I said, first of all, the low energy Hilbert space is much smaller. It is effectively only 1 spin-and-a-half degree of freedom for every 2 Majorana modes, which is a weird thing. And again, if the sites are far apart, no local observable can distinguish between these states in the Hilbert space, unlike in the magnetic case. The energies that are, of course, precisely degenerate if they're infinitely far apart. If there's a finite separation, again, just like in the magnetic case, there is a splitting. So they're not, strictly speaking, zero, but the splitting, again, falls off exponentially as e to the minus r over c, where c is some microscopic coherence length, and we'll have to talk about what that is. So again, if the distances are 100 times c or something like that, then the exponential is completely negligible, and we can say that these are really completely degenerate. Now, in theoretical discussions, people often take this limit where e to the minus r of c is 0. And that's what we'll mostly be talking about. We're using that language, but you have to remember that in practice, when you realize this in a real system, you may not be able to get these Majorana modes so far apart that this is completely negligible, because c, although it's a microscopic length, it isn't necessarily angstroms. For example, in most of the examples we're going to be talking about, it's a couple of hundred nanometers, so a couple of tens of nanometers, or something, it could be a couple of hundred nanometers actually. So you have to get pretty far apart to make these things really negligible. Nonetheless, this is the motivation, and theoretically, this is what we want to talk about largely in that limit. Okay, so now the question is, why are they interesting? Well, if there's some way of moving the location of these defects around, then you can do weird things with these. In particular, what people are interested in are moving them around what they call adiabatically as a function of time. That means it's not technically really adiabatic. It means that motion is very slow on the scale of the frequency of any excitation, finite energy excitations. So in that sense, it's very slow. On the other hand, it has to be fast on the scale of these exponentially small energy splittings. Otherwise, the degeneracy is not good enough. And so, but the point is, as long as it's slow on the frequency scale of the energy of the finite energy splittings, you'll stay in this low energy Hilbert space, and when you move these things around each other, and you suppose you interchange them, you change the initial positions except for a return to the original positions, except for maybe some interchange of the sites, then the final Hilbert space is the same Hilbert space as you started with, and so the result of this manipulation has to be a unitary transformation in this Hilbert space, as long as you don't mix in anything outside it. Now, the thing that's interesting is that these unitary transformations in general don't commute. The final state depends on the order in which you interchange one particle, one of these things around each other, and so you can manipulate from one state in this Hilbert space to another, and as long as you're doing it on a rate that's fast compared to the splittings of these exponentially small splittings, the results are completely insensitive to the route that you've taken, except for the topology of the braiding of these things. So it's a very robust control over the Hilbert space, and so people have, they say that therefore these manipulations are topologically protected, because you have to, the only way you can change, go from one to another is by changing the topology of the braiding. Of course, that's neglecting these exponential terms, which are not necessarily right. And so this has been inspired. People have thought, well, with topologically protected manipulations, maybe you could do quantum computing this way. And in principle, you can have very long memories, and you can do a lot of manipulations, but you can't, it turns out that you cannot do a set of manipulations which is actually can realize all the necessary ones for a complete quantum computer. So there are big obstacles, even in principle, for using using these states for quantum computing. It may be combined with other manipulations, could be useful, but in practice, this is a very long way away. And that's not the reason why I'm going to be talking about this. I'm more interested in it because I think it tells us something very interesting about the physics. Okay. All right, so where can we find systems with point defects that support localized Majorana states? Well, the first example that was proposed is something called the fractional quantized Hall state at filling fraction 5/2. It's a highly correlated 2D electron system in a strong magnetic field, and there was a wave of there was a Hall plateau observed there in 1987, and gallium arsenide heterostructures. It's now been observed in a few other places, and the wave function for this even denominator state was propositioned by Moore and Reed in 1991, which is a very exciting thing that implied that there are localized Majorana states, which are associated with the defects in this case are the elementary charged quasiparticles, which are charges that have 1/4 of the electron charge. And people have been looking for this. So various numerical calculations suggest that the 5/2 state should be of this Moore-Reed type, and therefore should have these Majorana states. But so far, experimental evidence has been difficult to be concluded. There's some evidence for it, and some evidence that's not so easy to interpret. But I think I'd have to say that the evidence is far from conclusive, and it seems to be very difficult to actually do anything with these. Even if they're there, they seem to be very hard to control in this particular system. So that's not where most of the focus is today. And there are a variety of other systems where people have proposed that this can occur, and particular point vortices in 2-dimensional, certain kinds of 2-dimensional topological superconductors. Again, there are a variety of different proposals for realizing this in 2-dimensional systems. Most of these are hybrids, again, of superconductors and various other materials. But so far, the experimental realizations are mostly lacking. The thing that's most promising are the 1-dimensional variants of this thing, in which you're trying to produce what's called a 1-dimensional, quote, topological superconductor. And if you can produce one, and again, these are largely hybrid structures, if you can produce a topological superconductor, then the defects that we're talking about are they're going to be their boundaries in one dimension. A defect would be a wall between a topological superconductor and an ordinary superconductor, or a topological superconductor and the vacuum, an empty state, or also if you have a junction where two of these wires meet in the shape of a T, then there's going to be also there's a defect where they meet, and there's a Majorana state at that defect. And we'll see what you can do with those. So the proposal here is to have a semiconductor nanowire with strong spin-orbit coupling. You need an applied magnetic field in certain directions, and it should be in tunneling contact with a bulk S-wave superconductor. And there were several people who proposed this more or less simultaneously in 2010. Oregon et al., J. Sau et al., the Maryland group, Potter et al., and Andrew Potter and Patrick Lee at MIT. And there's some related ideas that date back for quite a while, but they're all not exactly the same. Okay, so what is a hybrid structure? So the hybrid structure is, this is a schematic view cutting through the end of it. So so this is this is my nanowire and indium arsenide or indium antimonide are the two candidates that are the most used. Whoops. It's like the light has died here. Okay, but do you have a stick or something? I hope you're going to give me an extra 30 seconds for my talk. Okay, thank you. Okay, so here's the wire. This is a superconductor, which we consider a bulk superconductor. It may actually not be that much bigger than the wire, but if it's a metal, it has many, many more electrons in it. So we want it to be thick enough so we can think about it as a bulk superconductor, an ordinary S-wave superconductor. And this whole thing is sitting on some kind of an insulating substrate. And in many cases, we want to have a gate, a metallic gate underneath, so we can use that metallic gate to change conditions, let's say contain the density of electrons in the wire. And there's a magnetic field which can be applied in this direction, or it could be applied along the length of the wire. And there's also an internal electric field, which we don't have to apply, but which is always there, because you have you may have charges on the top here and not on the bottom. There's always going to be some asymmetry between the top of the wire and the bottom of the wire. That's very important from a symmetry point of view. Okay, and the semiconductor should be narrower than the magnetic penetration depth, but wide enough so that we don't have random spin flips. And this is just the edge view of the same thing. So you see here that the main thing is you can see the gates. There may be split gates, so that different parts of the wire can be, you can increase or decrease the density in different parts of the wire. Okay, and so now, as I said, what we're actually going to be interested in are not individual wires, but networks of wires, which have been proposed as a way of doing manipulation, and a number of Alessia et al., Clark et al. Proposed ways of doing it, and we propose some more general ways of doing these manipulations. And there are a whole variety of ways of doing the manipulations. I'm going to just talk to you about the simplest one, but they always require some kind of junction between more than one wire. So okay, so here's the basic structure. It's a T junction, where three wires come together, and I haven't shown, this is a top view of it, and I haven't shown you the gates. And by varying the electric charge on the gates, we're assuming that we can fill or empty different parts of the wire. That's the simplest thing. So red segments are filled, and we're filling them so that they're in a topological superconductor regime. And I'll tell you later how you get to the topological superconductor regime, but let's assume we can do it. I just want to show you what we can do with them. So the green segments are supposed to be, the dotted green segments are depleted of electrons. So now we can have straight or wire or bent segments, and as we've said, there should be a Majorana mode at the end of each filled segment. So here we see Majorana mode here, A, B, C, D, E, F, G, H. Those are all Majorana modes. Okay, so there are 8 of them here. Now, I also, if you have a T-junction, you have 3 Majorana modes at the end, and there's a fourth Majorana mode in the middle. So you can see there's always going to be an even number of Majorana modes. Okay, so now in order to do something, we want to move these Majorana modes around each other, so we have to be able to manipulate them. So these are the basic manipulations that I need to do something interesting. So the first thing is I want to be able to interchange the Majorana modes at the end of the same wire segment, A and B here. And it's going to matter what direction I do it in. So here's a way of doing it with a clockwise direction. By depleting the gates, and by changing the charge in the gates, I move the segment to be that way. I move it there. Now I move it there. Move it there. Here we go. Right? We've gone around in a clockwise direction. We're exactly back where we started from. So we've made a certain transformation, unitary transformation in Hilbert space. Okay, but that's not good enough. I also want to be able to interchange Majorana modes on different segments. So I want to interchange B and C here. How am I going to do that? How do I interchange B and C? How can I do that? Well, again, I do that. Now I do that. Okay, so B is attached there. Oops. Now I break it apart. So now B is attached to D. And there I am. I've done it. I've interchanged the 2 of them, and I've done it again in a clockwise direction. Okay, great. Those are the basic manipulations. Now I want to do an experiment to see something interesting. So to do an experiment, you first have to initialize, then you have to manipulate, and then you have to measure to see what's happened. So initialization. Start with an empty wire and change the gates on it so that I'm now putting, say, positive charge on the gate, and I'm pulling electrons into the wire, and I'm going to produce a superconducting wire segment out of nothing, out of the vacuum. Okay, and finally I make this, I start with it very short, and now it's long. I want to be very long compared to the superconducting correlation length. And so when I make it long enough, there's going to be there'll be a pair of Majorana modes at the end of each of these wires, at each end. And we have electrons in the wire. And there are electrons all the time now tunneling in and out of the wire from the superconductor. So the number of electrons in this wire segment is quite, if it's long enough, there are a lot of electrons going in and out. The number of electrons is very, it's not a good quantum number. It's average, there's some average density, but that can vary continuously. On the other hand, the electron number parity is fixed because I can only, I'm assuming the superconductor is a good superconductor with an energy gap, so I can only tunnel pairs of electrons, Cooper pairs, in and out. So I started with no electrons in it, so I know what I've done is I've produced a wire segment which has an even number of electrons in it. The electron number parity is even. I don't know how many it is. It might be 1,000, 1,002, 1,004, maybe oscillating all the time, but it's even. Okay. Now, measurement. So obviously, what I'd like to do is measure whether a wire segment has an even number or an odd number. Right? So this way I've prepared it, has an even number. Maybe I do something crazy to it, inject an extra electron, it's odd. I'd like to know whether it's even or odd. So what do? I reverse things. I contract I contract it and I change the gate potential so that eventually I completely deplete the wire. There are no electrons left. Now, if there's an even number of electrons originally, they go in group of pairs and nothing weird happens. On the other hand, if I had an odd number of electrons to begin with, then at the very end I have one electron left in this nanowire. Now, because there's a big energy gap to the superconductor, it's hard to get the extra electron into the superconductor. In order to do that, I have to apply a lot of extra negative voltage. So there's extra energy. It costs me more energy to get it in. And if I could measure how much energy it takes to get the last electron in, I would have a measurement. This is not necessarily the best way of doing it in practice, but in principle, it shows you that it's a measurable quantity. And so let's not worry about practice. Let's just try to understand what we want to do in theory. So we can measure, by getting rid of the electrons in the wire, we can measure whether they're even or an odd number. Okay, that's what we just said. So the measurement determines the electron power. Okay, so now for an interesting experiment. Let me start with a situation where we have two wire segments, each of which is prepared the way I told you, so they have an even number parity. Right? Now we're going to do, I'm going to do a manipulation in which I interchange B and C by exactly the way I told you in the clockwise manner. And then I'm going to do it again. So now it's back, A, B, C, D. It looks like I've returned to exactly the state I started with. But I claim that if I do this, and I'm in the topological regime, so everything is separated, so my time scales are exponentially long, and I'm doing it fast compared to that, what I'm going to wind up with is, instead of having an even number of electrons in each wire, I'm going to have an odd number of electrons in each wire. And then I can measure and see that I've changed things by doing this manipulation. That's pretty weird. If I did it so that I first did the interchange in a clockwise manner, and then did the interchange in a counterclockwise manner, you would think, well, that kind of is going to undo this winding back where I started with. And in that case, I claim I would find that if I made the measurement, I'd be back with positive plus plus. So it matters which direction I've done this manipulation. Okay, so what's happening in between? So what's the state when I've only interchanged C and B once? So then I claim what I'm going to get is something, so now it's a state. What if I measured the state now after interchanging it just once? So I have A, C, and B, D. I claim in that case, if I would measure it, I would find, well, not surprising, 50% of the time I'd find plus plus, and 50% of the time I'd find minus minus. The total parity can't change, so I can't get plus minus or minus plus. They either have to be plus plus or minus minus. That's the only two possibilities. And there'd be a 50% probability for each of them. But it's not an incoherent. The important thing is that this is what the state in the middle there is a coherent superposition of plus plus and minus minus. They're added together with a definite phase factor. And the fact that it's coherent, well, that means that the phase factor, I said for the experiment to depend only on what I've done and not how long it took me to do it, it means that this phase difference has to be independent of time, even for the pure systems, but even has to be independent of time, even if there are an airplane flying by or somebody walks by carrying an electric charge in their pocket. It has to be completely insensitive to the environment. And that means that the only way that can be is because that means that the state in which the wires have even parity and the state in which they have odd parity cannot be distinguished by any local measurement. For example, the even parity state and the odd parity state have to have exactly or exponentially exactly the same charge density everywhere along. It seems weird, but it's possible because you have electrons going in and out all the time. So we could have a state which has on average 1,000 electrons in it, which is like an even number, but that could be made up of 1,000, 1,002, and 998, or it could be equally well 999 and 1,001, and if it's fluctuating back and forth and you have a wide distribution, you can't tell. There's no, if it's fluctuating rapidly, there's no way of measuring whether it, what the exact number is, and the energies are the charge density is very much the same whether it's even parity or odd parity. That's the key.
Bert?
Yeah.
I mean, no one asked any questions, so maybe I should.
Please, yeah.
Right. Is the statement about robustness, is it a zero temperature statement? Or temperature?
Yes, we're talking about, sorry, I should say we're talking about zero temperature, or temperatures low enough so that we have not excited any extra states in the above the energy gap. You still can't you can't distinguish between even and odd, but if there are, let's say, if the temperature is high enough, say that there are quasi-particles in the superconductor, then a thermally excited quasi-particle in the superconductor could tunnel into the wire and change the parity. So then you'd have to do your manipulations on a time scale that was fast compared to the time it took, on average, some thermally excited quasi-particle to tunnel in from the outside. So that would be...
so the errors would be exponential.
Errors would be, yeah, so again, they're only exponentially small if you go to low enough temperatures below the gap. So that's also a problem, but in practice, actually, I think where we are now, it's usually possible to eliminate the thermal things much better than the overlap. The biggest obstacles presently are obstacles to getting the Majoranas far enough apart. But eventually that could be a problem. Yes, okay. All right, so as I've said before, some more comments. Are there other questions, by the way? I'm sorry, please. This is a good time to ask questions.
Does it matter when you have one exchange, whether it's counterclockwise or
yeah, so the difference between exchanging it clockwise or counterclockwise is a difference in the phase. One might be, say, an even combination, and the other an odd combination. It depends on how you normalize things. Or one is I and the other is minus I. And if you reverse it, you get a different phase. Okay, and the phase matters because you're going to eventually do another manipulation. If you don't do any other manipulations, you don't care about the phase. And you just get 50-50. But if you're going to do another manipulation, what happens after the manipulation matters very much what the phase of this combination is. And anything that would destroy, anything that would give you a random phase, because it could distinguish between even and if there was some way the environment distinguishes between even and odd, it would then give you it would randomize the phase. There'd be different energies for the two states, so you'd randomize the phase between the two combinations. Then you have an incoherent superposition, and then no matter once it's incoherent, no matter what you do, you're going to just wind up with 50-50 mixtures. Yes.
Could you please return to the detailed explanation of how switching B and C works? Yes.
This one, do you? So, okay. So
Yeah. The previous slide before that, I had a question about this. This one. So in practice, we have one more defect in this picture because we have a corner in the AC line.
the corner is not a defect.
Not.
That is it. So the corner in general would not produce a Majorana state, or if it did, it could produce a pair. If I were to say, suppose I were to break this, you could say, what happens if I actually broke the wire over here? Then I'd have two Majoranas. But those two Majoranas would be very close together, and so they would be strongly interacting, and a pair of Majoranas, as we'll see, will not be a zero. Once they're close together, then the energy is splitting, it's split by some large amount, and we're assuming that that amount is large enough so that we're fast compared to any such splittings. So if you may produce some extra states During the manipulation, you may well produce some extra states that are below the superconducting energy gap, but they should always be still, there's some minimum energy, and you have to be doing things that are fast compared to h bar over that minimum energy. So there could be other, but there are always, any other states are produced, any other defects are produced in pairs, and the pairs have to be split. Question?
Yeah. I also became curious about this part because when you, I imagine when you do it realistically, those pairs can be produced in this or that moment, and therefore you're talking about the couple, and therefore the big energy they're not filled, right? The states, but can it be the case that, for example, the state B that we were interested in keeping will couple to that pair, and some other state will come out of it, and like we will lose information somehow?
Yes. So no, that's a good question. So it turns out it doesn't matter. So yes, you can produce. There may be there might be an intermediate time when there are 3 Majoranas close together. Oops. Yeah, so at this point, let's say there might be 3 that are close together and they're all interacting. But if you take, if there are 3 states, and we'll look at it when we look at the math a little bit more, but if I have 3 states, 3 Majorana states that are coupled together, there'll always be one energy state that has some positive energy, say E, another one that has a negative energy, minus E, and 1 0. Okay, and so there always remains 1 0 energy state, and the phase is kind of controlled as you go through these manipulations. It's actually complicated to see exactly what happens, but there is a conservation law, so it always works out. Yeah.
If I bring B and C close together, like not completely close, say, well, I guess the point is I bring them close enough that I decide.
So suppose I make B and C, oops, be back. You mean by bringing the wire down so that it touches?
I mean, so if I go back to like the starting state of this, where I have A, B, C, and D like just on the one line, and I bring, or even like this, and I was able to, rather than just, I guess I was able to shift the gates so I effectively move B and C so that their overlap's non-zero. I lose topological protection and I start to make a gap form.
Correct.
This gives me something. Now, if I leave that for a certain period of time, this picks up a phase. Does that act as a sigma z on like the logical state that you're doing a rotation on here?
Yeah, it's some uncontrolled rotation.
Right. So if I do that, can I get universal quantum computation when I lose by sacrificing some protection or not?
No.
No. Okay.
Oh, I'm sorry. Yes. I'm sorry.
Oh, okay.
Yes. I'm not sure if that one will do it. I think that one won't do it. But yeah, if you're willing to sacrifice, if you're willing to sacrifice topological protection, yes, you can get universal quantum computation, and that's the hope, that you can do maybe most of your manipulations using topologically protected ones, and then a relatively small number of non-topologically protected ones could be, you do them very carefully and in a controlled manner. Maybe that's a way of getting there. Yes, absolutely right. Yeah.
What's the topological charge of this?
Sorry, say it again?
What is the topological charge of this?
Charge. I don't know. So there's a Z2. The topological charge, I think, that what it's talking about is the can people hear me all right? The question is, so the topological charge, he asked. So I think one would say that if I have a superconducting wire segment, there's a topological quantum number which is a Z2 number. It's either, let's say, 0 or 1. 0 would be the non-topological state, and 1 is the topological state. So that's, I think, the way I would identify the topological charge. I think that's, I don't think there's a topological charge associated with the Majoranas themselves.
Can I ask one more?
Yeah, okay.
The space difference that you get when you do clockwise and anti-clockwise, just to make sure it doesn't give us any way to distinguish right hand from left hand in that sense.
I don't think so, because it's only after doing some number of them that you can tell.
So it doesn't define those right chirality, left chirality, only different.
I'd have to think about that. Maybe there is a way. We should talk about that. I don't think it does, but maybe there is a handedness. So I think not. I think that's a question of a gauge definition. Okay, so let's see. Okay, so just again, so an isolated segment will always have in this model as a fixed electron parity. If you want to change the parity of a wire segment, you have to bring it together with another one, so you can interchange parities between them. The total electron parity is always conserved during these manipulations. So if a wire segment has a definite electron parity, if you rotate it or interchange the ends, obviously that has no physical effect on the wire itself. It doesn't change the parity. But if the wire is in a coherent superposition of two parity states, then if you interchange them, you do get you change the phase factors relative to other things. So that the even and odd states can get different phase factors if you do an actual manipulation. But this is not a local manipulation. We have to move the electrons a large distance in order to do that. Okay. The third thing is that you can actually also change the phase if you change the phase of the superconducting order parameter in the superconducting couples to the wire by 2 pi. That will also change the phase difference between even and odd parity states, and that can be done if you have, say, if you have a vortex in the surrounding superconductor, and I move that vortex around the wire segment, that will change the parity. So that's equivalent to some. That's also kind of topological manipulation that could be used. And you can also make 3-dimensional networks of these wires with T-junctions into something like a jungle gym. You have these things connected, and it's possible to do manipulations there. The rules are a little bit more complicated, and that's one of the things that we've looked at, but I'm not going to talk about that. Okay, so I was going to pause here for questions, but I think people, the questions have been asked, I hope. Okay, so now we're going to talk a little bit about math. How do you describe these Majorana modes, and also to talk a little bit about the relation or the non-relation of this to the concept of Majoranas in Majorana fermions in elementary particles. So the mathematical description of a localized mode is, as we said, it's a peculiar zero energy defect, degree of freedom bound to some defect which has some specified position Ri, and with each of these defects we associate mathematically an operator gamma I, which is often called half of the Majorana operator, is often called half of the normal fermion operator. The properties of these operators are, if you have gamma I and gamma j on different sites, they anti-commute. The gamma I, gamma j is minus gamma j, gamma I. But unlike the usual raising and annihilation operators for fermions, gamma I squared is not 0, but it's 1. Gamma I is actually is a self-adjoint operator. Gamma I dagger is equal to gamma I. So that's why people would say often that the annihilation operator is the same as the creation operator, or sometimes it's said that the particle is its own antiparticle. This is what it means. But you can combine two Majorana operators to give you a normal fermion operator. If I have two sites and I define an operator C which is gamma 1 plus I gamma 2 divided by 2, and C dagger is, of course, gamma 1 minus I gamma over 2 over 2. Then if you calculate, if you go through the math, and you multiply C times C, C squared is equal to 0. And C dagger is not 0, and C dagger plus C dagger C, the anti-commutator, is equal to 1. And that's just exactly the rules for an ordinary raising and lowering operator fermion. So this has the same eigenvalues. C dagger C has eigenvalues 0 and 1, so you can say the state C is occupied or not occupied. Or we can take for combination 2C dagger C minus 1, which has eigenvalues 1 or minus 1. And we can say that we can call that the parity of the pair, it can be either plus 1 or minus 1. And this operator, you can see, is just equal to I times gamma 1, gamma 2. This is an emission operator. This gamma 1, gamma 2 is an anti-emission operator. And so the whole thing is, what we're saying is that if the sites Ri and Rj are very far apart, there's no energy splitting. That means that energy does not depend on the parity of the pair. It doesn't depend on C dagger C. But of course, if we bring them close together, then there can be an energy splitting between the state where the parity is even and the parity is odd. Okay, and so the history of this, so why is it called Majorana? So in 1937, Majorana realized that a neutral fermion in relativistic quantum mechanics can be its own antiparticle. And he hypothesized that this may apply to the neutrino. And whether the neutrino is a Majorana particle or not is still an open question, very much of interest to particle theorists. And the experimental test to try to determine whether a neutrino is in fact a Majorana particle is by looking for something that's called neutrino-less double beta decay. That means the nucleus can emit 2 electrons and 0 neutrinos. And that's possible only if the neutrino is a Majorana fermion. And basically what's happening is that ordinarily when an electron is emitted, a neutrino is emitted, but here what happens is you emit two electrons come out, 2 neutrinos come out virtually, but they annihilate each other before the electrons escape. So all that comes out is 2 electrons, and there's no other particles, so they should come out with exactly an energy that's very precise. And so if you can measure the energies coming out, we would find some peak at this energy. This has not been seen, but it's a very difficult experiment. The event rates for double beta decay are expected to be very small, proportional to the for this neutrino-less double beta decay, it would be very small, so it's not necessarily surprising that it hasn't been seen. But there are people who are trying to look for it. But I just want to say that even if they find it, there's a very big difference between a relativistic Majorana particle and what we're looking at. Because even if it's possible, first it's very hard to localize a neutrino. Even if we could localize a neutrino, it wouldn't have these weird characteristics because, first of all, it has a spin, so there'd always be an even number of localized Majorana modes at the same position in space, and then if you were to somehow move one around the other, it wouldn't, all these pluses and minuses would cancel out. So it's not really, there's a mathematical relation, but no real physical relation to the Majorana.
Question?
I remember hearing something along the lines of neutrinos needing to be massless in order to be Majoranas. Is that
Massive?
That have to be massive to be Majoranas?
Yeah.
Okay.
Well, that may not be true, but if they don't have a mass, it may be completely impossible to decide whether they're Majoranas or not. But we know that neutrinos do have a mass, and the question is whether it's a Majorana mass or whether they're...
What about the charge?
Of which?
The high energy Majorana.
No, but they're neutral, but they have a spin. So the neutrinos have a spin, they're chargeless. They have to be chosen. Okay, so how do we get topological superconductor? How am I doing with time?
Yeah, 10 more minutes.
Okay. So we have a single, so here's the model again. I'm going to simplify. Let's say an indium antimonide nanowire that's sufficiently thin so it has only one, there's no transverse mode, so the only degree of freedom that I'm interested in is the position x along the wire, and it also has a spin. And so let's just think of a single electron in a wire. So it has some kinetic energy, p squared. I'm not going to worry about the mass. There's some v of x which confines the electron so it doesn't run off the end of the wire. There's a potential v of x which is, say, 0 in the middle of the wire, but it goes up to plus infinity at the two ends of the wire. And then it's very important that there's a spin-orbit term we're not going to, of the Rashba type. So it's proportional to this electric field there's an electric field in the z direction, momentum in the x direction, times the spin in the y direction with some coefficient alpha. And then we're going to apply an external magnetic field B in some arbitrary direction, B dot sigma. I'm going to have some wires oriented in the x direction, and the E field is in the z direction. We can ask, what does the spectrum look like? So if I have no magnetic field present, but I do have, obviously, I'm going to be very, let's say the wire is infinitely long, then of course it would have a parabolic spectrum, but because I have this term here, which is linear, and sigma y commutes with the Hamiltonian, we have basically two different spectra for sigma y equals +1 and sigma y equals -1, and they're just parabolas that are displaced by some amount. So they overlap at p equals 0, they're degenerate, but the minima are not at p equals 0, they're off separated. And now suppose I have a magnetic field that I put on, let's say the magnetic field is in the z direction, and the two states here that are degenerate would then be split, okay? And so here we have two states, the higher energy state, let's say, had spin in the plus z direction, this has spin in the minus z direction. But then far away, the magnetic, once I'm far away, where this term might be big, the z splitting is not important. And the states here, a state here would be mostly oriented with, here, this state would have sigma y positive. Well, here it would still have sigma y positive. There'd be some small admixture of sigma z as well, or a large admixture, depending on how large the spin-orbit coupling is. Okay, and now, so now we want to couple this to a superconductor. It's a bulk superconductor, and we're going to describe this by the Bogomolov-de Gennes Hamiltonian. So this is a Hamiltonian which you double the Hilbert space by adding electrons and holes, and you get a Hamiltonian which is basically H1 plus H2. H1 is the single electron Hamiltonian that we've talked about before, but double because you also have to have a negative in the holes. And then there's a pairing term which describes the process in which Cooper pairs hop from the superconductor onto the wire and off it. And if a superconductor, if a pair, let's say, hops from the wire onto the superconductor, that's produced by some amplitude annihilation operator for a spin-up electron, annihilation operator for a spin-down electron at some point r, multiplied by basically something proportional to the energy, to the phase and energy gap of the star of the superconductor. So you get a pairing term like this, plus the Halperin conjugate, which adds the electrons. So, and since it's an S-wave superconductor, you can only remove a pair of spins that are opposite to each other in an S state. Now, what we want to do is adjust the Fermi level. Let's assume that the pairing is weak, and we'll adjust the Fermi level to fall in the wire so that it falls inside the energy gap at p equals 0. That is to say that at zero momentum, the lower energy state is filled and the upper energy state is empty. And if there were no superconducting, then the band structure would just look like we showed before. And there are two Fermi levels. There are 2 points where the energy crosses the Fermi level. One over here at positive kF and minus kF, and there's no Fermi level here. And H2, of course, it's going to introduce a gap, and it only affects states close to the Fermi level if the gap is small. And what it's going to do, what H2 will do is, of course, create a pair of electrons, let's say one of them here and one of them here. They have to have opposite momentum, and they have to have opposite spin. Okay, now this is a little bit of a problem, because if we had a large Zeeman field on, these would all be spin down, and these would be spin down, and there would be no coupling to the superconductor at all. But as I said, there's some admixture. The state here is some admixture of, it has a component of sigma y, which is opposite in these two, and sigma z, which is not. So you can project, you just take out the piece that has proportion to sigma y, and then you can make a pairing here. But of course, if the Zeeman energy is large, or the magnetic, if P is small, then there's only a very small fraction of the state that has in the sigma y state, and so the energy gap that's induced here will be reduced relative to what it would be otherwise by this factor of basically the ratio of sigma y to sigma z, which is, it's reduced by a factor of P, basically divided by the magnetic field. And the thing that follows from this is that here, if we're in such a state, there would be an energy gap here, energy gap, everything. So there's an energy gap, but this is a good superconductor with an energy gap. On the other hand, if I were to raise up the, and this I would claim is a topological superconductor. It's a situation where we have only an odd number of states at the Fermi level, and we've paired them. And what happens here is that there's an energy gap. Now, if I were to move the Fermi level up here, there would be 2 states, and I'd have, it wouldn't be, now it has an even number of states. If I were to produce, if I were to cut this, that you could say, well, I produced Majoranas on each end, but there's a pair of Majoranas, and they would couple to form an ordinary electron state, so it wouldn't be topologically protected. And if I want to go from one to the other, I could raise the Fermi level, and you can see that what happens here is as the Fermi level hits this point here, now there's no energy gap anymore, because now the Fermi level, there's a zero energy state over here. We're measuring those states relative to the Fermi level. There are 2, there's a spin up, there's a single zero energy state here, but it can't couple to anything because there's no way that you can't inject a pair of it. Or if I were to try to take 2 states very close to this and couple them to the superconductor, well, they have the same spin, so it doesn't work. So what would happen is that the energy gap of this system will vanish if I try to go from the topological state to the normal state. And that's the characteristic of these topologically protected states. If I look at an infinite system, it has an energy gap, and that energy gap, if it's a topological or not topological, in order to go from one to the other, there has to be a vanishing of the energy gap. And that's, okay, so that's why this is protected, and I think, well, maybe I won't talk about exactly, how much time I have, 5 minutes? Or? Yeah, so, okay, I was going to talk about the mathematics of how you diagonalize the Lejeune Hamiltonian. Normally, the Lejeune Hamiltonian has states occur in pairs. One has positive energy and one has negative energy. They also have to occur in pairs. And the only way you can get something that's at zero energy, there has to be, the only way you can have a state that's not paired is to have a state at zero energy. Then E and minus E are the same. If I have a semi-infinite wire, I can have a zero energy state at one end of the wire, and that's my Majorana state. If I have 2, then there are 2 zero energy states, and if they don't overlap, they're still at zero energy, and that's my 2 Majoranas. And I was going to talk about how that occurs, but I think I can't say much more about it. And the robustness is partly because these states have to always occur in pairs. The only way I can get rid of a pair of Majoranas is by bringing them close enough together so that they overlap, and then they can split into a positive energy state and a negative energy state. And that's basically what we were talking about before. Experimental evidence. So the best evidence is for these indium antimonide or indium arsenide wires, and probably the first most dramatic evidence was produced by Moerik et al. The Koevenhoven's group in the Netherlands, and this just shows you the scheme in which you have different gates and wires and with a superconductor, niobium tin nitride superconductor, and whoops. I'm missing the experimental slide. So the slide got removed. But anyway, they looked at tunneling into the end of the wire and saw without a magnetic field on the wire, it's the state, we needed a magnetic field, so without a magnetic field, the wires are normal, you're inducing superconductivity in the nanowire. If you tunnel into it, there's an energy gap where you have very low conductance. And once they put enough magnetic field on, they started to find a signal with very low energies where you could tunnel from the, you're tunneling electrons from this, here there's basically a kind of barrier here, you're tunneling through the barrier into this superconducting, induced superconductivity, and they saw a zero energy mode, and from B greater than 150 millitesla, which they identified as a Majorana state. There's a lot of questions about whether this is really necessarily a Majorana state or not, and just having low energy doesn't guarantee it. But there's now some evidence that that this is the case. So, of course, in some sense, they're always Majoranas. It's almost a trivial question because every electron is a superconductor. Every electron can be written as a superposition of 2 Majorana states. So if you have electrons, you have Majoranas. The point is that if you have a topological superconductor, the Majoranas should occur in pairs always. And these pairs should be at the opposite ends of the wire. But you could have defects if you had a non-topological superconductor. There might still be Majoranas, but they'd be in pairs. They wouldn't usually be at very low energies, but maybe for some reason they would be at low energy. There's things called Andreev bound states that could have very low energies. But if you think of those as a Majorana pair, the pairs are close together. So what you'd like to show is that if you have a Majorana, where is its partner located? Is the partner nearby or very far away? That's the question. And as we said, the energy splitting of a Majorana pair, it should fall off exponentially with the length of the wire. Actually, it doesn't just fall off exponentially, it also oscillates. So if you were to say calculate, it's a finite length wire, what's the energy splitting between the even parity state and the odd parity state? That's what the splitting between the Majoranas are. You would find it goes something like exponential e to the minus x over c, where c is the superconducting correlation length, which is typically about 200 nanometers in these wires, times the cosine of kfxx. Kf is the Fermi wave vector, and what that means that it does something like this. And the interpretation is if E is positive, that means that the ground state has an even number of electrons. If E is negative, then it has an odd number. You see it's oscillating. For short wire, it oscillates by a large amount. As we get to larger and larger amount wire lengths, it doesn't matter whether it's even or odd, so these oscillations decay. And the question is, can that be seen? And I think some of the best evidence that we really are seeing Majorana pairs at the end of the wire are measurements that were done in Charlie Marcus's lab a year ago in Copenhagen, and this shows you the energy splitting measured by tunneling, or the energy when you tunnel into one end, as a function of applied magnetic field, and effectively by varying the magnetic field, you're varying the correlation length and KF. And so here you're in the non-topological state, so there's a big energy gap, which is like 70 millivolts. And then if you go to the topological state, then you see these oscillations that we were talking about here as a function of the magnetic field. For a short wire, these oscillations, they're relatively large. Here's a longer wire that's 1.5 nanometers, and you can see that the oscillations are much smaller. And what Charlie measured, 5 different wires of different lengths, and he was able to fit the amplitude of these oscillations to something that looked like constant times the length minus the length of the wire over c, and lo and behold, it did fit to an exponential. Yeah, and with a correlation length that was 250 nanometers, and it sort of fell off by a factor of 100 from the shortest wire to the longest wire. So that's looking pretty good. And I think that's sort of the best evidence that we're really there. Okay, so, oops. Okay, so let me just stop the summary and ask more questions. Please.
I was just wondering, you say that the experimental studies are still ambiguous. Can you tell us what experimental evidence there is for it?
I was talking
sorry,
about the
five
halves.
fractional quantum Hall state.
Yeah, so the question is, what's the experimental evidence that's ambiguous for Majorana existence in the 5-half state? So the experiments for it, there's really no negative experiments, it's just absence of experiment. The experiment that was been cited as evidence for it are some very pretty experiments, very fascinating experiments done by Bob Willett, in which it's kind of a little complicated to explain it, but they're interference experiment. It experiments in which you have a small superconducting island, a small island of 5 halves. You prepare something 5 halves, and you have there are gates, and you pinch it off so that there's a small island that's connected on 2 sides to leads. So it forms what's called an interferometer, and you can inject a pair. You can, so you're looking for oscillations in the conductivity as you vary, say, the magnetic field, or vary a gate. In his case, he's varying a gate, and you're looking at the period of these oscillations. And if you neglect, if you had a very large sample, so that you could neglect these exponential factors of tunneling from one end to the other, then what was predicted is that you should have a change in the period. You could have a period of oscillation that corresponded to half a flux quantum or a quarter of a flux, or a charge of E over 4, a charge E over 2. And you would go back and forth from one to the other depending on how many quasi-particles there were inside the interferometer. And lo and behold, he does see some ranges where there's a period of corresponding to E over 2, and other where it goes E over 4 and then back. And so superficially, this looks like a dramatic confirmation of what's going on. But there are 2 problems. So one is no one else has actually been able to duplicate this, so that's one problem. The second problem is that if you start saying, well, what about the effect, the size of his dot, or the size of his interferometer is some fraction of a micron, and there are many quasi-particles in it. So the distance between the quasi-particles is, or the Majoranas, is probably less than 100 nanometers for sure. And if you predict if you ask, what's the decay length, it's tens of nanometers. So you're not going to get you get a few factors of E, and he's making measurements over a very long time scale. So if you try to make an estimate of what the effect of these the fact that the Majoranas are overlapping, he should be in a regime where they're strongly overlapping, and then you can't understand, no one has been able to explain his results in a coherent way, assuming that there's a lot of, or in a convincing way anyway, assuming that there is overlap. So somehow either there's no overlap for some reason that we just don't understand, or the experiment has a much more complicated explanation that we don't understand. So that's why I call it ambiguous. That's the only, he's done several different, he's looked at different samples, and the data looks good, except he has to average over a very long time in order to see anything. And so let's say rival experimentalists in general don't feel that the experiments are convincing from an experimental point of view. And as a theorist, I just have a problem understanding why it should work in these geometries. That's what the situation is. And no one has been able to improve it. It's very hard to work with these interferometers. Other people have not seen any interference at all. Who tried to do it, they've just not seen anything. And, okay, so Willett says, well, you're not careful enough. You have an average long enough. He's averaging over minutes or hours.
More questions? Yeah, please.
You mentioned that an electron is a kind of combination of Majorana fermions, right?
I'm sorry, I couldn't hear.
So you mentioned that the electron is a superposition of the Majorana fermions.
Well, I guess you could say it's, yeah, okay. Yes.
And the electron has self-integer spin. So what's the spin of the Majorana state and how they add up to form the spin of the electron?
Oh, okay, well, so there's a magnetic field on these, so these Majorana states are superpositions of states that have, each Majorana state is a superposition of a state with spin in the x direction and a spin in the minus x direction, or it's some weird direction. It depends on, but each Majorana state is a superposition of a spin in one direction and the other. So the Majorana has, the average spin is zero, just as the average charge is zero. But now you take a superposition of two of them, and you get rid of the part that's, say, in this direction, and you have, by taking the superposition, you wind up with something which has a spin in just, let's say, the x direction, and it has a charge. And the question of what direction the spin is depends on which end of the wire you're looking at and what the orientation of the wire is, the orientation of the magnetic field. So the Majorana is a it's really, think about the Majorana as a sum of an electron and a hole. Okay. And the electron in the hole, the electron has a charge and it has a spin. The hole has the opposite charge and the opposite spin. So the net is zero. But when you add two of them together in a coherent way, you get the interference term, which produces the electron and the hole. It produces an electron or a hole depending on the phase in which you add them together.
Thank you very much.
More questions? More questions? Am I allowed to ask?
There's somebody behind you.
Oh, sorry.
Maybe a stupid question. It's interesting whether tunneling between two Majoranas is a local process or non-local?
Okay, so it's certainly not a stupid question. I would say it's non-local because there's no way of knowing where the tunneling has occurred, and moreover, let's say if you add an electron, well, yeah, so if I look at, if I bring the Majoranas close enough together so there's some overlap between them, and then I can produce the two different states, which are the even and odd states, and there's some difference between them, and they would have a charge density as well, but the charge density is not localized at one end or the other, but in fact it's really uniform, or neither is it localized at both ends. With the extra charge would be spread over the entire wire almost uniformly, because the charge comes from interference, which is the product of an exponential that's decreasing and an exponential that's increasing, and the product of the two is something that's actually doesn't change. That's more or less constant along the wire. So I would say they're really very delocalized. The tunneling takes place everywhere, because if the tunneling is like, the amplitude is the product of two exponentials. One's decreasing, the other's increasing, and when you take the product, it's constant. But it's actually a very good question, and one that has caused a lot of confusion.
More questions? Yeah, so can I ask, given that there are many people here working on magnetism, I want to ask about other kinds of Majoranas. I mean, there are these Majorana fermions that Onziger used in his solution of two-dimensional Ising model. And that's probably the second time they appeared after Majorana himself.
Yes, yes.
In physics, and and they also occur in pairs, because in the Ising model, the main walls appear in pairs, and in many ways they're similar. They are Stackmerk, but if you go to quantum Ising model, you also get quantum Majorana fermions in solution of the quantum Ising model. So how these Majorana fermions are fundamentally different from the ones you talked about?
So the question is, so you want to say localize your domain walls, so my question, I guess, would be, I haven't thought about so could we say make the question is, could you do some kind of manipulations? Let's say I had a bunch of so we want to talk about 1 + 1 dimensions, I guess, Ising models in 1 + 1 dimension, and let's say I made a T-junction or something. And would there be ways of manipulating the domain walls that would produce some kind of topologically protected manipulations? That's the question, I think. The question is there some topologically protected manipulation that can be done? I don't know. That's a very good question. We should think about it. I don't offhand see, but it's possible that maybe we could do. Maybe there is something.
No one thought about it?
No one told me about it. Anyway. They thought about it. Maybe if they thought about it and found something interesting, then we would know about it. If they thought about it and didn't find anything interesting, they might not have bothered to write.
Of course. Yeah. Last question. Yes.
So, when the original Delft experiments came out, a lot of, I think not everyone was convinced, because there was all this question about Andreev bound states, etc.
Well, and people
still not convinced.
Many other explanations for
yes.
A lot of zero bias anomalies, and people talked about Kondo and this and that. Yes.
So I guess my question is really, for your personal opinion, have you been convinced yet? And at which point, if so, at which point were you convinced? And if not, what would make you convinced?
Well, so the thing that's most convinced me are these Charlie Marcus experiments. As I said, the question, to my mind, the question of whether it's a Majorana or not is irrelevant, because I'm convinced it's a Majorana. The question is, where is the other pair, the other member of the pair? And just having a low energy doesn't necessarily mean that the pair is at the far end of the wire, because as you could see, you can get oscillations, and you could just hit the right length where it didn't care whether it was even or odd. The more experiments that are done, the less likely these other experiments are. But I find that the Charlie's experiments, to me, are pretty convincing that there's a state with its pair at the far end. There may be other Majoranas in the middle of the wire, that there may be other localized states in the gap, there may be disorder, but at least those states are high enough in energy that they're not interfering with the splitting of this pair at the bottom. So I think that's correct. Now, whether you can do anything useful or not, it means that this is not good enough. E to the minus 10, so he has a factor of 100, which is e to the minus 4, or whatever, 5. We need at least another couple of factors of 100, I think, in order to really be able to do anything useful. And of course, people will really be convinced when someone can produce a T-junction and actually do some of these grading experiments, at least with 70% fidelity or something like that. So I'm pretty convinced that it's there, but I'm not convinced that it's useful.
Thanks.
Last call. All right. Thank you, Bert.